Thank you everyone for joining me for today's video on ellipse. It's a type of a conic section. I'm Mr. Ish. As you remember previously we've discussed circles already, and we've also talked about parabolic sections. These are all components of conic sections, and they're all important topics when it comes to precalculus. Today we will talk about ellipses, but in a general manner. If you think about a circle and you draw a circle, let's just draw a circle with a little center over here. And let's draw two axes which bisect each other at 90 degrees. If supposedly you look at this first line of axis going horizontally, and we'll call that A1 hypothetically, and we look at this other line of axis going vertically, both of these are going right here through the center, we call this A2. Now remember, for a circle, whenever you draw these are basically called chords. A chord is a segment which goes from one side of the curve to the other side, but always through the center. But if you look at both of these chords in a circle, right, and they're going through the center, both chords must be equal because they both represent a diameter. So both of these chords are equal in length. When we're talking about ellipses, and if we were to compare similar chords, A1 will no longer become A equal to A2. The reason being, the ellipse, which is an extension of the circle, it will be eccentric. Alright? The ellipse will be eccentric, which means it will be less circular, or it will have a certain skew to it. So there will be a certain characteristic of eccentricity in an ellipse, whereby you end up having the two different lines of axis no longer being equal. You end up having a major line of axis, and you end up having a minor line of axis. So let's draw a representative ellipse. Here's our center, and let's look over here. Now you see there's a little bit of eccentricity. The shape is oblong, it's not purely circular. If you look at this one line of axis, and you call this A1, and let's look at this one, we call this A2, now you can clearly see A1 is greater than A2, just visually. Even though I've not drawn it to scale, you can visually see that the A1 segment major axis is larger than A2, which is the minor axis. So A1 here is called the major axis. Actually, let's not even bother writing it. A1 is called the major axis, and A2 is called the minor axis. So this fundamental difference between the circle and the ellipse must be kept in mind as we examine this conic section. So keep the difference in mind between the major line of axis and the minor line of axis. The major line of axis will be the segment that will go to the longest part of that shape. The minor axis will go to the shortest part of that shape. You see here, clearly this is the longest part of the shape. From this end to this end, it will be the longest axis. From this top end to the bottom end, you'll have the smallest axis. So keep that in mind. But what exactly is an ellipse? Like circles, there's a center. We can call that a center, C for center. But then you also have two additional points. These are called focus, right? Or in plural, you can say foci. But these are two foci within an ellipse. The fundamental characteristic of an ellipse is this. If you put a point anywhere on this curve, so you see this is a curve, anywhere on this shape, if you put a point over there and you connect it to these two foci, the entire distance of this will always be constant. What does that mean? If you draw another point anywhere on this shape, this ellipse, and you connect it again with the two foci, this here, the distance of this new set of lines will be equal to the set of the original set of lines, which means the distance is always, let's call this F1, the distance is always constant, and let's call this point 1, and let's call this point 2. So if you look over here at this point 1, if you measure the distance from point 1, P1 to F1, if you measure that distance P1 to F1, and then you add that to P1 to F2, it will equal some constant value. But now look over here at point 2. If you look at point 2 and you measure the distance from point 2 to F1, you take that distance and you add it from point 2 to F2, it'll again be equal a constant value, but here the thing is the k's are equal. The distance will always be equal, that's why it's called a constant. So an ellipse is a set of points on the curve or on the ellipse such that when you always calculate the distance from that point to both of those foci, they're always equal. So that's the definition of the ellipse. I want to examine equations of the ellipses because there will be 4 types of equations you should be familiar with. There's always a standard form, then there's that extended form. We'll look at the standard form first and we'll bring in the extensions as we go into this topic. Let's look at the standard form of the ellipse such that the center of the ellipse will be at the origin, alright? The center here in these equation forms will always be the origin. Remember, as I was talking earlier about the major axis and the minor axis? Well, there are 2 types of equation forms depending on which axis is the major axis and which axis is the minor axis. Remember, the major axis will be longer than the minor axis. It's the more eccentric part of that ellipse. If the major axis happens to be in a horizontal direction along the x-axis, right, and the minor axis in the vertical y direction, you have an ellipse which looks something like this. You see this, an oblong circle, but the major axis is in a left to right direction, the minor axis is in the up to down direction. Here the equation form will be easy. It's x squared over a squared plus y squared over b squared is equal to 1. What a and b represents I'll talk about momentarily. So keep this in mind right here. For the major axis in a horizontal direction, you have this form, and let's just write here as abbreviation major axis M capital A in a let's say plus and minus x direction, which means horizontal. If the major axis now happens to be in a vertical direction, which means you'll have plus and minus y value changes, then your form or your conic section will look something like this. Now the major axis is in a vertical direction and the minor axis in the horizontal direction. Here your equation form will become this: x squared over b squared plus y squared over a squared is equal to 1. Look at that difference. The a over here represents the major axis values. Okay, major axis values are represented by a, the letter a. The length of this axis is always 2a, because if this right here is minus a comma 0 and this right here is a comma 0, the distance from the origin to this point is a, but the distance of this total is 2a because you're doubling it. You're doubling it over here. Look over here. Here the major axis in a vertical direction is 0 positive a, and here 0 comma minus a. Here you have a major axis in a vertical direction, but again the major axis over here length is 2a. The minor axis is represented by the b values. The minor axis, let's use a lowercase m and a capital A. Minor axis is represented by the b values. Here you have 0 comma b, but here you have 0 comma minus b. The distance of course over here can be 2b, always from the origin to the b, double it. Over here your minor axis is in a horizontal direction, so you have a minus b comma 0 and you have a b comma 0, but here the minor axis is going to be represented again by the letter b. So keep in mind, depending on your a values, which are always your major axis values, if the major axis value is directly placed below the x value over here, x squared value, you know you're looking at a horizontally major axis ellipse. If your a is placed under the y, now you're thinking about a vertically directed major axis. That's the difference you need to be aware of. But what about those points I was talking about, the foci, the focus? The focus is always located within an ellipse. Where in relation to an ellipse, it depends on the style of your ellipse. And by style I mean, is the major axis horizontal or is the major axis vertical? If the major axis is horizontal, and we're talking about here with the origin being the center, your foci or the focus points are beneath or inside these A points. These A points are called the vertices, alright? The vertex of a ellipse is represented by the A's, the major axis. The end of the major axis represents your vertices. The foci are always located within the vertices. And the foci, the focus points are determined by means of calculating the C value. And I'll tell you what the C value is. C value can be over here in an x direction, or C value can be in a y direction. Here you'll have C comma minus C comma 0 plus and minus C comma 0. Here you'll have 0 comma plus and minus C. So the foci can be either like this, plus and minus C comma 0. These are for the horizontally directed ellipses. Or the foci can be 0 comma plus and minus C for the vertically directed ellipses. How do we actually calculate C? Well, you need to know A and B technically, and C will always be C squared is equal to A squared minus B squared. If you know what A and B are, use them through this formula and it'll give you your value for C. Again, this represents the schematic for an ellipse which is located in a center about the origin. This side over here, horizontal major axis, this over here, vertical major axis. The minor axis here is in a vertical direction and the minor axis here is in a horizontal direction. Now let's look next at the ellipses when there is translation occurring. Now I admit that what I'm showing you over here may seem like quite a bit, like you're thinking about parabolas and circles, and now this seems like several steps above all of that. Yes, I admit all of that there's a lot to keep in mind over here, but it's not hard. Because as you start going through the examples, you find out it's actually pretty easy. But when we're talking about ellipses which are no longer centered about the origin, we have a different equation form which comes in, but it's not hard because it's something you've already seen with regards to circles. Look over here, x minus h whole square over a square plus y minus k whole square over b square is equal to 1. Now look over here, you've got horizontal shifting and you got vertical shifting, but remember for ellipses you'll always have a plus in between. There'll always be a plus no matter what the formula, and there'll always be a 1 over here no matter what we're talking about. With ellipses you must always have a plus here and you must always have a 1 over here. Now look over here, I have the x component here and the a component together, which means we're talking about here a major axis. The major axis is in a horizontal direction. You see, the major axis here is in a horizontal direction. Your graph may look something like this, an ellipse with what are horizontal vertical shifting, but it'll be in this direction, right and left ellipse. But if the equation form was this, x minus h whole square over b square, you see the change of b square, plus y minus k whole square over a square, and a square is always a larger value, b square is always a smaller value. Larger because a will always represent your major axis, the longest segment or the chord within that ellipse, and b will always represent your minor segment. But again, it's always equal to 1. Here we're talking about a major axis, capital M, capital A, major axis, but in a vertical direction. Your graph will look something like this, an ellipse which is in this direction but centered about this center, but in a vertically major axis direction. The minor axis will always be opposite and perpendicular to that major axis. So look over here, nothing too drastically added here, but it's an extension of what you might already know. What else should we be worrying about when it comes to ellipses? Keep in mind this, as I mentioned previously, but perhaps briefly, c squared should always be a squared minus b squared. You know, if you got your a and your b values, you can calculate the c, and the c here will represent your focus. Let's just use foci. The foci will always be either plus or minus c comma 0 in a horizontally directed ellipse, or it can be 0 comma plus or minus c in a vertically directed ellipse. But again, look over here, these zeros indicate that we're talking about an ellipse centered around the origin. But when we're talking about over here, now you have to consider it's not just going to be plus and minus c comma 0 or 0 comma plus and minus c, because we're no longer about the ellipse. You'll take your, based on the types of centers you will have, you'll adjust the focus accordingly. Let me show you how you will adjust it accordingly. If you have a focus which looks something like this, h comma k, and we're talking about a horizontal major axis. If you're talking about something like the horizontal major axis, look over here how your focus point will change. Once you've calculated your c value, you'll be h minus c comma k, right? And then you do h plus c comma k. You take here, this right here is your h comma k, your center. Remember, h comma k represents your center. And you know, when your major axis is horizontal, you're looking at this equation over here, and your foci or your focus points are always located within your vertices. The vertices are always the endpoints of your, let's use v. The vertices are always the endpoints of your major axis. Okay, in this form over here, if this is your center, right, you're going to do c units in this direction towards the left, and you'll do c units towards the right direction. See, h minus c, and you do h plus c, but there'll be no change to your y value because we're moving right now in a horizontal direction. We're talking about here about foci, your foci units. Now if supposedly your ellipse is in a vertical direction where you have a vertically directed major axis, and we're talking about an H and K as a center, but for a vertically directed ellipse, now look at how you'll determine your focus over here. Remember, all easier when you see examples. It will be H, comma, K minus C, and your other one will be H, comma, K plus C. Now your foci will be determined based on your Y coordinate because your movement is long and parallel to the Y direction. So keep these changes in mind. More difficult to appreciate it when you're seeing letters, but much easier to appreciate it when you're looking at actual examples. Okay, again over here, your vertex will be here, one vertex here, one vertex will be over here. Your minor axis will be in this left to right direction, your major axis will be in an up to down direction. Your foci will fall somewhere in between. See, the foci here will fall somewhere in between. You'll have a center, so keep in mind this. Let me show you. For any ellipse, what are the directions? You'll have a center, you'll have two foci, let's call these F and F. You'll have two vertices, let's call this V1 and we'll call this V2. So you have to keep all of this in mind. You have a major axis going in the largest direction of this, or the longest direction, then you'll have a minor axis going in the smallest direction. So you have to look at all of these components from your equations. Before we actually look at examples, I want to present one last concept for ellipse, then we will look at some examples. Let's talk very briefly about this one concept of eccentricity. Eccentricity is symbolized as E, and it is calculated by taking the ratio of C and A. You know C you can calculate from having the values of A and B. You square them and then you take the square root of that difference, you calculate C. But what exactly is eccentricity? Eccentricity is basically just a measure of how close to a circle the ellipse resembles. If it's very circular in appearance, it will have a low eccentricity. But if your eccentricity is so far deviated from a circular form, it will look highly eccentric and will look very oblong. Look over here at these two examples. If this is a circle and this right here represents my one focal point, here's my other focal point. Let's not even call this a circle, let's call this a very circular ellipse. Now look, the C value is always determined from the distance of the center to the focal point. That's your C value. But what's your A value? You know all ellipses have a major axis. The end of the major axis represents your vertex. The A value is determined from the center up to that vertex. That's your A value right there. Okay, A value. If the ratio of C over A is very small, it's low, it's small, it will be more circular in appearance, right? It will be more circular. And it will be less eccentric. It'll resemble more of a circle and it'll resemble less of an ellipse. So it'll have low eccentricity. But if you have something which is visually quite oblong, here's your center, here's your focal point over here, here's your other focal point, here's your vertex, here's your other vertex. Now look over here, the C value is pretty large and the A value is also large. In this case, the C over A, the eccentricity is high. So your entire ellipse will look very eccentric, and you know this right here is your center, H comma K. Here in this case your ellipse will look less circular and it will look more oblong, meaning it will look more eccentric. The value ranges are basically from 0 to 1. Values close to 1 are considered eccentric, meaning the ellipse is highly eccentric, meaning it's more oblong and less circular. Values close to 0 are considered more circular, meaning your ellipse deviates less in terms of movement away from a circular form. It looks more circular and it looks less ellipsoidal. Alright? These are low eccentricities, these are high eccentricities. So this is just some extra dimension for you to worry about as you go through ellipse questions. And eccentricity is always C over A. Let's look at some examples. Before we look at practical examples, and our examples will just be of the general kind because we don't need to get too involved into this topic. This is just a brief survey. Look very quickly over here. We can have ellipses centered about the origin. You can have major axis in a horizontal direction, major axis in a vertical direction. For the major axis in a horizontal direction and an ellipse which is about the center, look at your equation form over here. For an ellipse here centered about the origin, major axis in a vertical direction, look at your difference in the equation over here. You have an a square over here under the y. Here you have the a square under the x. But again, you maintain the positives in all cases. Everything is always equal to 1 and everything always has the positive sign. This here is the positive sign right here. Another thing to focus on is down here. This equation can be represented in this form if you have movement about the origin. X minus h whole square over a square plus y minus k whole square over b square equals 1. Same thing over here. A vertically directed ellipse. You have translation going on over here, horizontal and vertical translation. All ellipses will have two vertices. Vertices will always be at the end of the major axes. Here you have horizontally directed vertices. Here you'll have vertically directed vertices. All ellipses will have two foci. Foci will always be located within and inside the vertex, the vertices within the curve. And you will also have to be aware of the center. The center here can be 0, 0 or it can be h, k based on the type of translation you have. Major axis will always be twice the value of a. Minor axis will always be twice the value of b. C square, which will be important in determining your eccentricity, will be valuable for determining, will be determined from a square minus b square. And remember, as I mentioned before, the c value will also represent your focus value. Your foci values will come from the c values. Alright? The c values are going to determine not just your eccentricity, but will also determine your focal points of the ellipse. So keep all of this in mind as we go through the questions next, and I'll present six types of questions actually, all building upon each other. They're not going to be hard, but you just have several things to keep track of. Here is the first question. Our question here is basically to determine the various elements of this ellipse. Now when you're looking at this, you should be cluing in over here. There's no x minus h, there's no y minus k, so we're looking at an ellipse which is centered about the origin. The center is going to be 0, 0. But look over here, and I always told you the larger value between a and b will always be a. You want to convert this into this form, x squared over a squared plus y squared over b squared. Why did I not say x squared over b squared and y squared over a squared? Because here clearly I can see the larger of these two numbers, which will always be a, is going to be 25 over here, and I know it's x squared over a squared. Therefore I'm looking at a horizontally directed ellipse, or horizontal directed ellipse. So write this in this form, x squared over a squared plus y squared over b squared equals 1. So just do that, x squared over 5 squared, because 25 is 5 squared, plus y squared over 4 squared. And I'm telling you, these questions are not hard. You just have several things to keep track of. So you know right out from here, a is equal to 5, b is equal to 4, and I told you c squared is equal to a squared minus b squared. If you do a squared minus b squared, 25 minus 16, and you square root that, you'll get c value is equal to 3. And you know c is determined to be helpful with regards to eccentricity and to the focal points, right? Eccentricity and the focal points. But by looking over here, we know very clearly our center is 0, 0. An origin directed ellipse. But what are our focal points? Focal points are determined from the c values, and we know we're talking about a horizontally directed ellipse. Our focal points will be several units from the center, 3 units on either side from the center, minus 3, 0, and I'm going to graph this all out, 3, 0. But what about our vertices? The vertices are the endpoints of the major axis. In a horizontal directed ellipse, the major axis is in a horizontal direction, and it'll be determined purely from the a value, plus and minus 5, 0, minus 5, 0, and 5, 0. And you know the major axis is also 2a. The length of the major axis is 2 times a, which is 2 times 5, which will be 10 units long. Look at the difference between a 5 and a minus 5. If you were to calculate the distance of this segment, it'll be 10 units long. What about our endpoints of our minor axis? Let's just say minor axis endpoints are determined from b values. But these minor axes are now in a vertical direction. Remember, the major axis and the minor axis are always perpendicular to each other. If one is horizontal, the other is vertical. Major axis here is horizontal, the minor axis must be vertical. And it'll be 0, minus 4 and 0, positive 4. So 2b, the length of the minor axis will be 2 times 4, which is 8 units. Do we have everything we need to characterize this ellipse? We do. Not to draw to scale, but here's my vertices endpoints right here, minus 5 and 5, 0. My minor axis endpoints, 4 and minus 4, 0, 4 and 0, minus 4. Let's connect them. My foci will be right over here, minus 3 comma 0 and 3 comma 0. My major axis is this, my minor axis is this. What's the last thing which remains? Eccentricity, which is c over here. How deviated is this from a true circle? Do c divided by a. We have 3 divided by 5, which is 0.6. So it's quite more closer to 1 than it is to 0, so it is more eccentric than it is less eccentric. So we have an eccentric ellipse over here. This was one example right over here. I don't think it was hard by any means, and everything was very well laid out for you. These initial questions are easy because you're given the equation form already. All you got to do is dissect that equation form. When we look at some of the examples later on, you'll have to create the equation form first, and you'll have to do completing the square technique. So what do we have over here? Let's put a 5 over here. Y minus 5 whole square over, let's bring a 25 over here. Remember, these always equal 1 when you have them in their proper form, always equaling 1. Now you can see we no longer have a ellipse centered about the origin because there's translation. But look over here, here's my a value. Remember, the larger of these two denominators is always your a. So we have something which looks like this: x minus h whole square over b square plus y minus k whole square over a square is equal to 1. So we now are talking about a vertically directed ellipse. A over here is going to be a 5. Remember, 25 is a 5 square. B is going to be a 3. C is going to be a square minus b square, and the square root of that. C is going to be a 4. Let's do a quick graph over here. What's my center? Your center is determined right here, h comma k. It's going to be 1 comma 5. Remember, think back to why these minus 1 and minus 5 translate into a positive 1 and positive 5. Because this thing is the same thing as saying x minus plus 1 whole square, and that thing is same as saying y minus plus 5 whole square. That's the only way you can retain the minus signs here, because you had a positive 1 horizontal translation and you had a positive 5 vertical translation. So your center is 1 comma 5. Keep that in mind. If our center is 1 comma 5, we can do rough graph over here. Let's say 1 comma 5 over here, nothing to scale, and we have a vertically directed ellipse. We know we're going to have movement along in a vertical direction. My major axis points are going to be determined from A points. 1 comma 5, I'm going to go 5 points down in the y direction. So my one vertex will be 1 comma 0. I have to go 5 units down. My other vertex endpoint will be 1 comma 10. Remember, I'm moving in a y direction, therefore I'm impacting the y value with the A. I'm impacting that y value with the a. So my vertex coordinates are 1 comma 0 and 1 comma 10. What about my focal points? They're going to be again in a y direction because they're always located within the vertices but in the same line of axis as the center. My focal points will be, you're going to move again along the y direction. There'll be 1 comma 5 plus 4, which is a 9. And 1 comma 5 minus 4, which is a 1. 1 comma 9 and a 1 comma 1. My focal points will be right over here and right over here. What about my minor axis endpoints? Minor axis endpoints. Now you know the minor axis is in a perpendicular direction to the major axis. You're going to move 3 units here and 3 units here about the center, but we're looking here at the x value because we're looking in an xward direction here. 1 minus 3 is a minus 2 comma 5, and a 1 plus 3 is a 4 comma 5. So those are your points. Let's draw these out. Minus 2 comma 5 will look somewhere here, and 4 comma 5 will look somewhere over here, and we'll have an ellipse which will look like this. But what about the eccentricity? The eccentricity is c over a. What's my c value? 4 over 5. 4 over 5, which is 0.8, quite a bit close to 1. So this is quite an oblong. It may not look visually oblong because I haven't drawn it to scale, but this will be an eccentric ellipse. Wasn't a hard question, it was actually an interesting question. Remember, c is from a square minus b square. This is my a square, this is my b square. The a square is always the larger value of the denominator. Always the larger denominator value is your a square. If it's under an x, you know you're looking at a horizontally directed ellipse. If it's under a y component, you're looking at a vertically directed ellipse. Keep all of these little points in mind. We look at a slightly different type of question next. Look at this question. There's a slightly different equation form. You're given something like this, which is in a totally non-standard equation form. You have to determine all the elements of this ellipse. And you know, when you're looking at something like this, you should be thinking about solving by completing the square, by isolating the x and the y components and taking everything else on the other side. Let's do that. Let's look over here at the x components. You have 9. I'm going to isolate 9 from this component over here. I'll get x squared plus 4x. And now I'm going to isolate 4 from this component right here. I'll get 4 into y squared minus 6y is equal to minus 36. Take 36 on the other side. Now complete the square over here. You should know how to do that by now. I've presented videos. X squared plus 4x plus 4. X squared plus 4x plus 4. I've completed the square over here. Plus 4 into y squared minus 6y plus 9. I'm not talking about the completing the square technique over here. You can look at that through a video. Is equal to minus 36. 4 times 9 is a 36. Bring it on the other side as a same sign 36. 9 times 4 is a 36. Bring it again over here as a 36. Minus 36 plus 36 cancel out. Do the completing the square. You get a 9 into x plus 2 whole square plus 4 into y minus 3 whole square is equal to 36. Remember, equation forms must always be, and now you're looking over here at translation, your equation form must always be equal to a 1. Alright? Divide everything by 36. Divide everything by 36. What do we get over here? Remember, we're dividing everything by 36 to make your ellipse equal to 1. Remember, the standard form is always equal to a 1. You get x plus 2 whole square. 9 divided by 36, you'll get a 4 down here. Over here, you'll get a y minus 3 whole square. 4 into 36, 9 times right here is equal to 1. Now look over here. We're beginning to get that equation form develop over here. We're having a larger denominator here and a smaller denominator here. This is going to represent your a value. And now, since a is under the y component, we're looking at a vertically directed ellipse. This is my a component, but a over here represents a squared, and this right here is my b component, which represents b squared. Therefore, a must be 3. B must be 2. What's c? A squared minus b squared. 9 minus 4. Square root of that, root 5. Remember, a squared minus b squared equals c squared. C squared is equal to root 5 over here. What's our center? H comma k. But this is a plus 2. The only way I could have gotten a plus 2 was if from my standard form I had an x minus minus 2, which negated the minuses and made it plus 2. So my center is minus 2 comma positive 3. Minus 2 comma positive 3. I refer you to my parabola videos to determine the h minus k and the h plus k, the translation effects. You can always review that. You know you have a vertically directed ellipse over here. Therefore, all the movement here will be again in a y direction in terms of your major axis endpoints. Your major axis is going to be determined from right over here. Your vertices will be minus 2, 3 units up and 3 units down. Minus 2 comma 3 minus 3 is a 0, and minus 2 comma 3 plus 3 plus 3 is a 6. What about my focal points? Focal points will be the result of interaction between the center and your c value, again in an up and down direction. You'll have minus 2 comma 3 minus root 5, and you'll have minus 2 comma 3 plus root 5. Remember, always certain units in one direction of the center and certain units on the other direction of that center. And look at that, it's beginning to take form over here. Looks good so far. What about your minor axis endpoints? Minor axis endpoints. If it's an up and down ellipse, minor axis is in the right and left direction. So we're going to go right and left of this x value, but by 2 units. It will be minus 2 minus 2, which is a minus 4 comma 3, y value will not change, and then minus 2 plus 2 on the other side. You'll have 0 comma 3. Eccentricity, c over a. C root 5 over a 3. Let's bring the calculator out. Root 5 divided by 5 square root divided by 3, I get a value 0.745. It is more eccentric and less circular, so this is an oblong ellipse again. You don't have to graph it out, but we can very roughly. Center is minus 2 comma 3, it'll be somewhere up over here. Your one vertex will be up over here. Your other vertex will be right over here. Let's connect these. 0, 3 and minus 4, 3. 0, 3 right over here and minus 4, 3. One focal point will be over here, one focal point over here. Remember, it's not drawn to scale. This is just a rough image, but you can see it's more oblong and less circular in nature. But this is this equation worked out to determine all the elements. The vertices, the foci, the minor axis endpoints. The vertices are your major axis endpoints, your eccentricity, the A, B, and C values, and the center. Check this question form out for a possible ellipse. When you're looking at something like this, which is going to involve completing the square technique, you know you're going to have transformation. I always isolate the x components and always isolate the y components. Look, we have 16x squared and 32x. Let's bring those together. 16x squared minus 32x. I have a 25y squared and 50y. Bring them together. 25y squared plus 50y. Take the 16 on the other side because you want to equal it something. Isolate from here and isolate from here and complete the square. You'll have 16 into x squared minus 2x. I'm leaving that opened up because I'm going to try to do things here in less space. 25 into y squared plus 2y is equal to minus 16. Let's complete the square. Minus 2x divided by 2 is a minus 1. Square of that is a plus 1. 2 divided by 2 is a 1. Square of that is a plus 1. 1 times 16 is a 16. Bring it over here. Always bring it on the other side of the equal sign in exactly the same way. 1 and 25 is a 25. Bring it over here as a 25. What do I get over here? These 16s will cancel out and you'll be left with just a 25. Let's erase it and put a 25. Just for the interest of saving space, 25. Look over here. I have an x squared minus 2x plus 1. It looks like a x minus 1 whole square. Let's do that. X minus 1 whole square. Let's create some space and write it over here. This completes into x minus 1 whole square. X minus 1 whole square. What about this y squared plus 2y plus 1? Looks very much like a y plus 1 whole square, right? Y plus 1 whole square. Let's write it out. 25 into y plus 1 whole square. Now we have completed and solved to the near completion point. We always have to equal it to a 1. Divide everything by 25. You always divide everything by that number, which will make your equal part into a 1. Always that number. The number here was 25, so therefore you divide everything by 25 because this must become equal to a 1. Now simplify all of this. This will cancel out over here. You'll essentially get this over here. X minus 1 whole square. I'm going to deal about this denominator momentarily. Plus y plus 1 whole square over 1. Remember 25 divided 25 is 1 is equal to 1. What do we do about here? 16 or 25? This is what you do. You write it as 25 or 16 because the only way 16 came up was you were dividing x minus 1 whole square by 25 or 16. Look over here. X minus 1 whole square, you're dividing it by 25 or 16. When you flip this around, you'll get x minus 1 whole square times 16 over 25. See, this fraction here will flip because you're dividing a fraction, you flip it, and you would end up with 16 over 25. But that 16 over 25 is the same thing as writing 25 over 16. The only reason why I'm even doing all of this extra step over here is because I still have to generate the a and the b values. I don't want to be having coefficients over here. So this 25 over 16 is larger than 1. Look at it. You have a larger number divided by a smaller number. This is going to be your a component. This will be your b component. But we have to determine what a square and b square are. It's x minus 1 whole square over 5 divided by 4 whole square. This is my a square plus y plus 1 whole square over 1 square, which is my b square, is equal to 1. Now you have everything laid out to actually complete this question. First thing, our center. Let's write CNT for center. 1 comma minus 1. 1 comma minus 1. A value 5 over 4. B value 1. C value is equal to a square minus b square. 25 divided by 16 minus 1 will give you a 9 over 4. C square will equal 9 over 4, which will equal, let's see, 3 over 2. Let's bring out our calculator to make sure we're not making a silly mistake over here. So we'll do 25 divided by 16 minus 1 and we'll square root that. I get a 0.75. So it's a 3 over 4. I was wrong. It'll be a 3 over 4. A value, B value, C value. And is this vertically directed or horizontally directed? I have the larger value here. 25 over 16 is larger than 1, or 5 over 4 is larger than 1. I have the larger value under the x component, therefore this is a horizontally directed ellipse. This is a horizontally directed ellipse. What is my center? It's 1 comma minus 1. What are my vertices? Vertices will be a values plus and minus from this x value. It will be 1 plus and minus 5 over 4 comma minus 1. What's 1 minus 5 over 4? 1 minus 5 over 4 looks like a minus 1 over 4 comma minus 1. What's 1 plus 5 over 4? 4 over 4 plus 5 over 4 will be 9 over 4 comma minus 1. Those are my major axis endpoints, the two vertices. What about our focal points? The focal points will be plus and minus 3 over 4 from the x component of 1 of this center, the x component, because we're moving in an x direction. It will be 1 plus and minus 3 over 4 comma minus 1. So that will be 1 over 4 comma minus 1, and it will be 1 plus 3 over 4, which will be 7 over 4 comma minus 1. How about my minor axis endpoints? Minor axis endpoints will always be in a perpendicular direction to your major axis. The major axis here is horizontal, the minor axis will be vertical. Now we're going to do the b value translations along the y value here. So it will be 1 comma minus 1 plus and minus 1. So what will we get? We'll get 1 comma, let's do minus 1 will be a minus 2, and 1 comma minus 1 plus 1 will be a 0. These are my minor axis endpoints. What about our eccentricity? C over A. 3 over 4 divided by 5 over 4. Cancel out these denominators. We get 3 divided by 5, which is a 0.6. So again, it's an eccentricity larger than half, so it's more eccentric and less circular. It will be a more of an oblong ellipse than it will be a circular ellipse. But here, everything is laid out. We just haven't graphed it, but very quickly, we can do a rough graph too. What's our center? 1 comma minus 1, right over here. What's our vertices? Minus 1 over 4 comma minus 1 and 9 over 4. Minus 1 over 4 comma minus 1 will be somewhere over here. Nothing drawn to scale, and here's my other point right over here. Our focal point 1 over 4 comma minus 1 and 7 over 4 comma minus 1 will be right over here and over here. Minor axis endpoints 1 comma minus 2 right over here and 1 comma 0 right over here. Here's my vertical, here's my major axis, right here's my major axis, here's my minor axis. The ends of the major axis are your vertices. The ends of your minor axis are these minor axis endpoints. These 2 points in between are your focal points, right over here, focal points. And eccentric ellipse. 2 more examples and we'll wrap this video up. This is a slightly different type of question where you're given bits and pieces of information and you have to determine the equation. When you're looking at this, you should be thinking the fact that we're developing zeros over here, we have an ellipse which is centered about the origin. Because you have movement along the origin over here. 0 comma plus and minus 8, 0 comma plus and minus 4. It could only have come from a 0 comma 0 center. Alright, let's write CNT, center. 0 comma 0. What should you do next? 0 comma plus and minus 8. Let's put that over here. These are my vertex endpoints, vertices. 0 comma plus and minus 4 are my focal point endpoints. And you know the focal points are always between the center and within the vertices. Right here and right here, my focal points. You know you're looking at something which is vertically directed. Vertically directed. The equation for that must be x squared over b squared plus y squared over a squared is equal to 1. Why is it y squared over a squared? Because the larger denominator value will be under the y component. Because you know you have a vertically directed ellipse. And this is equation form for something with an origin center. We have our a values and c values already provided. The vertices endpoints are always your a values. A over here is 8. C over here is of course your focal point, 4. So look over here, we have to determine our b value. We know we are given c value of 4 because that's determined right here from your focal point, and a value is 8 determined right here from your vertices. We know also the formula is c square is equal to a square minus b square. All you got to do is plug in these. C square is 16. A is a 64. A square is a 64 minus b square. When you solve here actually for b, you'll get a 16 minus 64, which is a minus 48. That minus will make that into positive 48, and you'll do a square root of 48. A square root of 48, which is what? 16 times 3, 4 root 3. That's your b value. You got your a value, you got your b value, and that's all you need, and you can finish this. It'll be x squared over 48, which is b squared, plus y squared over 64, which is a squared, is equal to 1. And here is our answer. If you want to be a little more creative, you can do determination of other items. Eccentricity is c over a, which is what? 4 divided by 8, which is what? 0.5. Equally eccentric, equally circular, right in the middle of 0 and 1. Remember, it's always, this right here is your range, so it falls right here at 0.5, right in the middle. But let's do some graphing over here. We know it's 4 root 3 is our b endpoints. For minor axis will be, our minor axis will be perpendicular to this. It will be plus and minus 4 root 3 comma 0. Plus and minus 4 root 3 comma 0. But what is exactly 4 times root 3? 4 times 3 root, just to give me a number, is 6.9. Kind of like saying it's close to a 7 right here. And your ellipse will look something like this. If drawn properly, it would have looked less ellipsoidal and slightly more circular, or somewhere in between both a circle and an ellipse. But right here, your question is done, and here's our equation. I want to present one more question of this type, and we will end the video with that. As our last question, this is what I present to you. We have the foci given, the focal points, and we have a major axis provided. From these two items, we have to determine the equation form for this ellipse. First thing you should be looking at is this. Major axis always has the formula that is always 2a. The major axis is twice the value of your a. If 2a here equals 12, a must equal 12 divided by 2, which is 6. Focal point is determined from either, for a center about the origin, it's always plus and minus c comma 0, right? Or it could have been 0 comma plus and minus c for vertically directed or horizontally directed. But you know the focal points is related to your c value. Just by looking at this, we know our c value is 5, because we're going to be 5 units away from the origin, either on the x-axis or on the y-axis. But here's on the x-axis because you're given the coordinates already. Plot these out. Plus and minus 5 comma 0. Here's my focal point 1, focal point 2. What about my major axis? I have a value of 6. If my focal point is along the x-axis, my vertices, which this represents your vertices, the vertex must also be in an xward direction, because the focal points must always be within the vertex and in between the center. So my vertex points will be right over here. One vertex here, one vertex here. And you know these points are minus 6 and plus 6 comma 0. So my vertices will be minus 6 comma 0 and 6 comma 0. And we can do c square is equal to a square minus b square and determine our b value. We know our c value here is a 5 square, which is a 25. And we know our a value here is a 36 minus b square. Let's bring out our calculator and solve for b. We'll have a 25 minus 36, which is a minus 11. But when you actually calculate for b, you'll end up getting a root of 11. Root of 11. What exactly does root 11 indicate? 11 root is 3.3. So somewhere 3.3 units up over here are my b values. Minor axis right here and major axis over here. Major axis horizontal, minor axis vertical. But we got to do more than just do this. We have to determine our equation. Our equation over here for a horizontally directed ellipse about the origin is this: x squared over a squared plus y squared over b squared is equal to 1. Always equal to 1. You just have to plug in the a and the b values. What's my a value here? 6. What's 6 squared? It's a 36. X squared over 36. What's my b value over here? It's root 11. Right? See, root 11, plug it right here into the square. And you will get root 11 square, which is an 11. And our question is done. X squared over 36 plus y squared over 11 is equal to 1. You want to be fancy? We can. C over A represents our eccentricity. What's our eccentricity here? 5 over 6. 5 over 6 looks something like 0.8 something. 5 divided by 6, 0.833. A very eccentric ellipse because it's very much closer to 1 and very far away from that 0. But look over here, 2 items provided and we determined everything. These things could have been away from the origin, then you would have had the x minus h whole square plus y minus k whole square, just a step above but exactly the same process. So be aware of ellipses and how they relate in terms of how their relationship is to the parabolas and circles. Some of the things which you studied over there pop up over here, but there are many new things which pop up with the ellipse. Not a difficult topic, but there's a lot in it that you have to know. Another pre-calculus topic. I hope you enjoyed this video. Please like, subscribe and share. Have a nice day. Bye.